Hi, myself Sheikh Irfan. The team members including me are Sheikh Irfan, Rishit, Harsha, Shivaram, and Namlish. Our team ID is G952. Our project title is Crystal Structure Generation using the autoaggressive large language models, enhanced version of it. So coming to the next slide, understanding the base paper Crystal LLM. So before discussing our point, it is important to understand the base research paper called as Crystal LLM. The main idea of this paper is to treat a crystal structures as a large language generation problem. Normally, large language models like GPT generate sentences or paragraphs, but in this case, the the model generates something called a CIF files. A CIF file, which stands for a crystallographic information file, is basically a text file that describes how the atoms are arranged inside a crystal structure. The model used in this paper is a transformer-based decoder model, similar to the architecture model in the large language models. It is trained using the millions of the CIF files, which are converted into the text sequences. One major advantage of this approach is the traditional methods, such as density function theory, which requires a heavy computational resources and can take a long time. But with this language model approach, the system can generate thousands of possible crystal structures within a few seconds. Simply by giving a chemical composition as input, this makes the process of discovering a new materials much faster and more efficient. So coming to our problem definition, although the crystal element model is very powerful, there are still some limitations. The first problem is data inconsistency. The training data used for the model comes from a different from different database and the similar resources. Each of these sources may use a different computational methods or settings. Because of this, the data may not be fully consistent and the model may learn the incorrect or noisy patterns. The second problem is the lack of the property prediction. The model can generate a structure of a material which tells us how atoms are arranged, but it does not tell any important physical properties such as stability, energy, or magnetism. In the real world material discovery, scientists need both the structure of a material and its properties. Without knowing the properties, it is difficult to decide whether the generated material is useful or practical for a real application. So coming to our project scope, to address these problems, we defined a real project scope. First, we will replicate the Brace Crystal LLM model architecture using the PyTorch. Next, we plan to improve the training process by introducing the conditional tokens. These tokens act like labels that tell the model which dataset or computation setting the data comes. This helps reduce the confusion in the training the data. We also plan to extend the architecture by adding a regression head to the model. This new component will allow the model to predict a numerical property, such as formation energy of the material. To verify the generated crystal structure, we'll use the PyMatGen library, which is commonly used in the material science. However, our project will not include physical laboratory experiments or web interface because our main focus is on the machine learning model. So, coming on proposed solution, our proposed solution is a multitask crystal LLM. In the original model, the system performs only one task, which is generating crystal structures as data. But in our improved approach, we convert the model into a multitask learning system. The first model is conditional generation. We add a special tokens at the beginning of the input data. This tokens helps the model to understand which competition standard or a data that belongs to. This reduces the noise and helps the model learn more consistent patterns. The second improvement is the simultaneous regression. In the final layer of the transformer, we add an additional branch. One branch continues the original task of predicting the next token, which generates the crystal structure. The second branch predicts a numerical value, such as formation energy. Because of this modification, the model will be able to generate a crystal structure and predict its physical properties at the same time. So coming up to the basic architecture diagram, first the input includes the chemical composition along with the conditional tokens. This input sequence is a process through several layers of a transformer decoder. This layers helps the model to understand the relationships between the atom and the crystals. At the final stage, the model splits into the two outputs. The first output predicts the next token in that sequence, which generates the crystal structure in the CI format. The second output predicts a numerical property of the material, such as formation energy. This architecture allows the system to perform two tasks at the same time, the structural generation and the property prediction. So, coming to our conclusion and the progress, to summarize our project, we explore how large language models can be used in material discovery. We analyze the base research paper, Crystal LLM, and identify the two major limitations. The first one is data consistency, and the second problem is the lack of property prediction. To solve these problems, we proposed a multi-task model that can generate the crystal structures and predict the properties simultaneously. So far, we have completed several important steps. We have studied the base research paper in detail and set up our development environment using the PyTorch and Codem, and explore the data acquisitions like tools like PyMatGen. In the next milestone, our goal is to replicate the base crystal LLM model run into successfully on our local systems to generate the crystal structures. Thank you. We hope that our project will contribute